Black holes are among the most fascinating and mysterious objects in the universe. Their immense gravitational pull, their ability to warp space and time, and their seemingly insatiable appetite for matter have captured the imagination of scientists and science fiction fans alike. But what does it really mean when we say that a black hole swallows everything? Is it true that nothing can escape its grasp, not even light? Or is this a simplification of a far more complex reality? To understand the nature of black holes, we first need to grasp what they are. A black hole is a region in space where gravity is so strong that not even electromagnetic radiation, like visible light, can escape from it. This occurs when a massive amount of matter is compressed into a very small area, creating a gravitational field so intense that the escape velocity exceeds the speed of light. The boundary surrounding this region is called the event horizon. Once an object crosses the event horizon, it can no longer escape or communicate with the outside universe. From the outside, it effectively disappears. But do black holes actually suck in everything around them? The answer is both yes and no. Black holes are not cosmic vacuum cleaners indiscriminately devouring everything nearby. If our sun were to suddenly collapse into a black hole, the Earth would continue orbiting it just as before, assuming the mass remained the same. That's because gravity depends on mass, not form. So, in that sense, a black hole doesn't actively pull everything in. It only affects objects that come close enough to its event horizon. Now, if an object does come close enough, what happens is far more dramatic. As matter falls toward a black hole, it often forms an accretion disk, a spiraling high-energy structure of gas and dust. This matter accelerates and heats up, emitting intense X-rays and other radiation that we can detect with telescopes. So, while the black hole itself is invisible, we can observe the energetic processes around it. One of the deepest mysteries surrounding black holes is what happens to the information of the objects they consume. According to the laws of quantum mechanics, information cannot be destroyed. However, if a black hole swallows a book, a star, or a person, and that matter is compressed into a singularity with no distinguishable features, it seems like all the information about its original state is lost. This is known as the black hole information paradox. Stephen Hawking proposed that black holes are not completely black. They can emit what is now called Hawking radiation, due to quantum effects near the event horizon. Over an incredibly long period of time, this radiation could cause a black hole to slowly lose mass and eventually evaporate completely. But what happens to the information then? Does it escape with the radiation? Or is it lost forever? Some theories suggest that the information is encoded in the radiation itself, though this idea remains highly debated. Others propose that the information is somehow stored on the surface of the event horizon in line with the holographic principle. Another suggestion is that matter and information that fall into a black hole may emerge elsewhere, possibly in another region of our universe, or even in a different universe, through what's called a white hole, or a wormhole. These remain speculative, but they highlight just how strange and counterintuitive the physics of black holes can be. In terms of what black holes can consume, the list includes gas clouds, stars, dust, light, and even time and space themselves in a sense. But it's important to emphasize that these interactions are governed by strict physical laws, not arbitrary devouring. The sheer violence of these interactions can, paradoxically, help scientists understand black holes. By observing high-energy jets, the motion of nearby stars, and gravitational waves from black hole mergers, astronomers can infer the presence and properties of these invisible giants. Black holes also vary in size. There are stellar mass black holes, which form when massive stars collapse, supermassive black holes, which lie at the centers of galaxies and can contain millions or billions of solar masses, and possibly primordial black holes which might have formed shortly after the Big Bang and could be microscopic or planet-sized. Each type poses unique questions about how matter behaves under extreme conditions. One particularly intriguing idea concerns the fate of the universe in relation to black holes. Some cosmologists speculate that in the far future, when stars have burned out and galaxies have dispersed, only black holes will remain. This so-called black hole era might last for trillions of years, after which even black holes will evaporate through Hawking radiation, leaving behind a cold, dark, and empty cosmos.